In this first workshop, we're going to look at how to follow the RoboCup line effectively using a PID algorithm as opposed to an on-off switch left and right. Just a quick note on the PID Controller Algorithm. It stands for Proportional Integral Derivative Control. It is used widely in industry in flow control and in car cruise controllers. You can find out a lot more about it in Wikipedia. Just type in PID controller. You will see the variables below KP, KI, and KD. You'll see these used along the way. K stands for constant. Yes, mathematicians can't spell. These variables will help us tune our code to make it run more smoothly. For all of my workshops, this will be the default layout of our connections. The left motor is in port B, the right is in port C, with the left sensor in port 2 and the right sensor in port 3, and the brick facing forward, as you can see. Once you become more experienced, you can choose how you want your own layout to suit your configuration of your robot. If you haven't done so yet, open up the EV3 Mindstorms education software and either start a new project or continue developing your RoboCup project. So let's get this robot moving. We will start by setting up and looking at the basic move codes to develop our program. Okay, we're going to begin with our basic move programs and the basics of our LEGO's education software. When you first open up, you'll get the action pan, the green ones. The next one across is the flow control, so it has wait, loop, switch, and other interrupts. The yellow is all of our sensors. The red is our variables and our mathematics. Blue is advanced things. And the aqua is where we can create our own blocks. So we'll start off with adding a loop into our program. So this will make the program continuously run until we tell the program to stop, or we can actually tell it to stop on a command or action. First up, we'll add in our motor tool. So there are 4 motor ones: medium motor, large motor. These 2 are both twin motors or multiple motors. This one uses a steering command, and this is a tank command, which independently controls the left and the right motors. Generally, we'll use the steering one, so we'll add one of those in. When we insert it, it starts off on rotation. You'll see there's either by second, by degree, or by rotation, and it's only set for 1 rotation. But what we want it to do is to continuously run, so we just turn the motors on. And this one will be our direction, and this is our speed. Up the top is which motors the ports are plugged into. Generally, if you've got your robot already plugged in when you start programming, this will come up where your motors are automatically plugged into. But you can click on them and change them. Now with our turn, when we click on it, we can either add a number or move the slider. So the more we move the slider to the right, it will turn to the right, and it's a positive finger. When we slide it back to the other way, it will turn to the left, and on the left-hand side is a negative figure. So we have negative on the left, positive onto the right. Now let's see how we can actually use that. Okay, so let's apply our move code to our mounted robot. When the turn variable is set to 0, both wheels will rotate in the same direction at the same speed. When the turn variable is between 0 and 50, the inside wheel, the wheel inside your turning circle, will rotate slower in cause the robot to make a slow, wide turn, like so. When the turn variable is greater than 50, the inside wheel will stop rotating and cause the robot to make a sharper turn, like so. When the turn variable is closer to 100 or 100%, then the inside wheel will turn backwards and the outside wheel will continue to turn forwards, causing the robot to do a U-turn and pivot on the spot, like so. We can also connect an external variable to our motor command and continuously change the variable to make our robot continuously change directions, like so, and therefore connecting our light sensor code to make it change the directions according to the light intensity. So let us now look at the light sensors and how we can use them. The ideal height for our light sensors is between 1 and 2 standard bricks away, or closer to 2. However, more than 2, green will start to be seen as black, and we may not be able to see the green in our challenge intersections. How do the light sensors work? What do they see? For this demonstration, we'll use uncalibrated sensors. We'll talk about calibrating a lot later. When the color sensor is set in reflective mode, it sees a light level as a percentage of white. Ideally, black is 0 and white is 100%. When the light sensor moves towards the black, the sensor value reduces, like so. When the light sensor moves from black to white, the sensor value increases, like so. Our RoboCup's robots will have 2 light sensors, and the light reflected reading should be even when it follows the middle of the line. Now when the robot moves right, light sensor 2 will see more black, and light sensor 3 will see more white, and the readings will go like so. When the robot moves left, light sensor 2 will see more white, and light sensor 3 will see more black, and the readings will end up like so. If we put these readings into a table, like the one on the right, it will look similar to like this. In real terms, the readings will be much more accurate, but to fit on this PowerPoint, I've only put 3 spacings between each one. At the top of the table, the robot is situated far left, and light sensor 3 reads more white, and light sensor 2 is reading more black. At the bottom of the table, the robot is far right, and light sensor 3 is seeing more black, whereas light sensor 2 is now seeing more white. And again, when the robot is in the middle, the robot is evenly seeing the light sensors of 2 and 3 almost identical. As we said earlier, the move steering motor block only needs one variable with a plus or minus. Plus will make it turn right to get back to the line, and minus will make it turn left to make it get back to the line. Therefore, light sensor 2, with 2 light sensors, we will need to subtract light sensor 2 from light sensor 3 to get the single plus or minus variable
as you can see in the outside line. The formula is going to look like this. Error, which is what we're going to call it, equals light sensor 3 minus light sensor 2 divided by 2. We use the brackets to make it calculate the subtraction before the divide. In a straight line, error equals 32 minus 32 divided by 2 equals 0, as shown in the table. This is called proportional control, and this is the defining the light proportion range of our light sensors. The code for this, our two color sensors, is going to look like this.
Okay, now we're going to create our EV3 code for measuring our light sensors. First, we start off with our standard loop. Plug that in. Now we're going into the sensors, and what we're going to select is the color light sensor. We're going to get 2 of those. It would automatically know what sensors are loaded, but it normally comes in with the first one. So we're going to run 2 on this one and 3 on the other one. You'll see why in a minute. Standardly, it will measure color, but we need to measure the light intensity reflected off of our service on both. So we change these to light intensity. Now, we're going to do a little bit of mathematics. So in the red data options, we see our variables, and we're going to do a little bit of mathematics. By default, it has a set of 2 variables that we can use. So plus, minus, divide. We'll go into the advanced, and we can get more complex on our. So we can have up to 4 variables on this. We're only going to use 2, but we need to create a different type of equation. And at the top, we can actually create our own equation. So as we've seen in the previous one, bracket A minus B, close the bracket, divide that by 2. So we're going to make it calculate A minus B and then divide it by 2. So that's our equation. Now we can take data lines. First we're going to get our 3, light sensor 3, put into A, and get our 2 and put that into B. So now it'll be A, which is light sensor 3, minus B, which is light sensor 2. And then we can work out the equation with that. Now we need to do something with that. We can go down and create a variable, put it in here. I've already got one earlier done, but we can create new variables, as many as you want. With this, it's in write mode. If we select on it, we can also use read mode. Further down the program, we will read the variable, but at the moment we need to write the variable. Instead of putting a figure into this, we can take another data line. So the outcome of the equation, we can insert that straight into the variable. So whatever the figure is here on the equation will make the variable change. As I said earlier, the variable will change and we'll make it change the direction. So that's how we create our light sensor.
If we want our proportional light sensor value straight into our motor steering block, as in the EV code before, this is what may happen. Our proportional error range is between 35 and minus 35. Remembering earlier, that's not enough turning power for a sharp curve or in corners like the animation, and you will end up overshooting off the course. When you convert the earlier table to a graph, we get a linear equation graph for a straight line, y equals mx plus b, where y equals a vertical axis and x equals a horizontal axis values. B is where y intercepts at x, 0, and m is the slope or the gradient. In our equation, b is always going to be 0. Therefore, we can change the equation to y equals mx. In robotics terms, this is called proportional control. Using our variable labels, x equals error. The bigger the error, the greater the turn needed. Y equals turn, the output value for the motors. M is a constant, which is K, KP proportional control. And this can also be called the conversion factor. The formula now is the code for our proportional algorithm with the two line sensors is going to look similar to the variables that were set up outside the loop. Otherwise, they'll continuously reset every time the loop cycles. Well, this might be a gain of 3, which is the KP. Our equation being turn equals KP times error, and therefore turn equals 3 times error, which will cause the robot to turn more sharply the further it is from the line. The robot, depending on the light reading, will move smoothly like this. Our table, it would look something like this. At the furthest end, this becomes better. Too far off the line, the robot will turn more sharply to get back onto the line. However, at the middle, this will cause more oscillation. The bigger the number, the faster the wiggle. The outcome will depend on the size of the gain used when we fine-tune KP. Too small, it will overshoot and stay in a straight line. Too big, it will oscillate and wiggle all over the place. Now to smooth out the bottom.